Okay, I think we are ready to go. Now I can hear myself. Yeah, when I now can see my slides, we can start. Thanks for coming. I know it's late and you had a coffee break, so it's all good. So it's okay to fall asleep. I will wake you up later on. Welcome to this session about what the CRaC, Superfast JVM startup. And I hope you can see it because I changed the colors of the scheme before the session because I had nothing better to do. So my name is Gerrit Grunwald. I'm working for Azul as a developer advocate. You can hear my voice is not the best, but I try to make it through the presentation. I'm also a JUG leader and first time here at JNation, and I have to say this is really a cool conference. Respect. If you would like to have the slides, you can get them here. Should work. I tried it. If not, just ping me on Twitter and then I will send it to you. They are online, also on SlideShare. Java is great. So first of all, who's doing Java here in the audience? Awesome. We have a vibrant community, as we can see, and we have hundreds of Java user groups. Someone here is a member of a Java user group? Just a few? I hope you have Java user groups here. You have to go there. It's just good. We have thousands of free open source software projects, but the real star of the whole ecosystem is the Java virtual machine, right? So the question is, how does it work? Well, I will give you a very simplified introduction on how the JVM works and only on some very small part that is important for this presentation. So you start with your Java code, which is in the source code, in your source file, in the Java file, and then you put it into the Java-C compiler, and this one creates a cross-platform class file out of it, right? So it has bytecode in there, and if you have a JVM on your platform, you can compile the bytecode to some native code, but we will look into that. So then we have the class file, and we use the so-called class loader, which is very simplified here, which is much more complex, and this loads the class file into the JVM memory. JVM memory, again, very complex, but this is just a simplified view. From there, it gets into the so-called execution engine, and you can see already that this is not only one thing, it has 5 different parts. And if we take a closer look at it, then you see it has, first of all, the interpreter, and then it has a C1 JIT compiler, formerly known as the client compiler. If you have gray hair, you know the client compiler. And then there's the C2 compiler, which is the formerly known server compiler. And then we have a profiler and a garbage collector. And the 2 compilers here also described often as so-called tiered compilation. And this is default since JDK 8. In JDK 7, it was the first time this appeared. And before that, you can choose the compiler you would like to use, server or client. So, but we will only focus on these 3 parts because that's important for the whole JVM startup thing. So what happens is the interpreter takes the bytecode line by line and interprets it into the native instruction set of the CPU, and the JVM is watching that, and it's counting method calls, right? So this is the smallest unit of optimization in the JVM is a method. So it counts these method calls until this reach a specific threshold. And then it takes this hot method and forwards it to the C1 compiler. That's the formerly known client compiler. So you see already, it compiles code as fast as possible, but with nearly no optimizations in it. The reason for that is, I already told you, it's the formerly known client compiler, and if you have something on a client like a desktop application, IntelliJ, NetBeans, Eclipse, you expect when you double-click the icon that it directly starts. You don't want to wait until the compiler really does his best compilation and 10 seconds later the window will pop up, right? So it should be fast. That's the reason why this compiler only compiles down to native code as fast as possible. Then again, this already compiled code will be profiled and watched by the JVM, and it's again counting method calls. And if it reaches another threshold, it will take this hot compiled code and put it into the C2 compiler. This one is much more complex. It's a quite old compiler. It gets updates over time, but it got harder and harder to maintain. But this one still produces the most optimized and fastest code in the JVM. So, but it takes a little bit longer, right? So that leads me to the execution cycle. This is in principle the same thing that we saw before, just in one diagram. So we start with interpretation, which is slow. And then we have this profiling phase, finding the hotspots. Then it goes into the C1 compile phase, again profiling this code, and then finally into the C2 compiler. After that, we should have the best optimized code ever, right? You see this other thing on the top left there. And this is de-optimization. Who knows what de-optimization is? One? Just one? Yeah? It's, not everybody knows that, but this is, first of all, it's a quite powerful tool in the JVM. On the other side, it can also have some performance hits for your application. So we will look into that. If we take a look at de-optimization, then, and we start with some code we have here on the left side. And on the right, I have some kind of a control flow. So you see there's a method, we pass in a value, we check if the value is greater than 9, and if this is the case, we compute something, and if it's not the case, if the value is not greater than 9, then the bias is equals 1 in this case, and then we calculate and return the math log to base 10 of the bias plus 99. You don't have to understand the code right now. The interesting part is if the compiler figures out that the value never was greater than 9, and it always went through this loop, then it says, you know what? I optimize it. I optimize the code to this, first of all. You see, we have now some other method called uncommon trap. This will only be called if the value is greater than 9, which is usually not the case, as the profiler figured out. So then we set the bias to 1 and then return this result. But we can even optimize that, right? We can just say, in this case, we can directly go, if it works, yes, to this one, right? Don't declare the variable. And if you know what that is, this is 2. So this is the optimized version, could be the optimized version of this method. And you can imagine that this is so much faster. And that will then run. And the problem happens if now suddenly the value is greater than 9. Then the JVM has to call the uncommon trap. That means this method, this optimized method, has to go away, so it will be thrown away in the trash can, and then it has to start all over again. De-optimization. Go back to the original method, do the interpretation, C1, C2 compile. You can imagine that this takes some time and that this is really a problem when it comes to performance. The code was already fast, and suddenly something happens, and it has to go back to the original version and has to do the interpretation and C1, C2 compile again. So this is branch analysis. If we take a look at the performance graph of the JVM, then you see these 3 colors, which is yellow in the lower left. This is the interpretation phase, and then we have the green one, which is the C1 compile and profiling phase, and then we get into the C2 phase, which is the blue one. And you see the performance increases until it reaches the maximum performance. Then we see some periodic gaps on the right side. This is typically garbage collection pauses. And no matter how fast your garbage collector is, there's always a pause. Even if it's just a millisecond or nanosecond, there is a pause, right? So this is these pauses. But then we see these bigger gaps in the beginning. And this is de-optimization. You see the code was already fast, and suddenly it drops, performance drops nearly to the bottom because it has to go back to interpretation and then C1, C2, and then back again to performance, right? So this is something you would like to avoid. I already told you that it could also be a benefit. Imagine the application behavior changes at runtime. Then with de-optimization, the compiler can throw code away and re-optimize it, right? Which is a big benefit at runtime, sometimes, not always. That's all great, but as we saw already, it takes some time, right? So just to give you an idea, because people, when they talk about JVM startup, they always make the mistake like, oh, the JVM is so slow. Startup time sucks, right? Especially when you talk about microservice environments and cloud deployments and these kind of things. So a little example is, just do yourself a favor, write a class with one method, system out println, start it, tell me it's slow. It's not. Because the JVM itself starts super fast. This is maybe 10 milliseconds. The problem that makes it slow is your code, which is clear, right? Because this is the stuff that needs to be interpreted and compiled and optimized and all that. So if we talk about JVM startup, then we usually talk about time to first response. And that totally depends on your application. You can imagine if you load everything in the beginning and initialize everything at startup, then of course it takes longer, right? There's a difference here. So if you talk about JVM startup, keep in mind that this always includes your application. And this is not everything, right? So this is JVM startup, but then time to first response doesn't mean your application is already highly optimized at that point. It's just the first time it responded. Means the application itself could also be optimized and warmed up, right? So this is JVM warmup, right? This includes stuff like you have to load data from a web service, you have to fill your caches, whatever, you name it. And this is then JVM warmup, right? And you have to make a difference between these things. If you hear people talking about it, then just be careful, because some people really mix everything up, right? So JVM start itself is fast, including your application, time to first response. This is JVM startup, depends on how much data you load in the beginning, of course. And if you like to warm up your application, then it's JVM warmup. People sometimes ask, why do I have to warm up my application? One example is we have a high-speed trading company as one of our customers. And what they do, for example, they stop every evening when the market closes, they stop their machines, and at midnight, they start again, and then they hammer their code with all kinds of tests and application patterns to make sure that at the morning at 8 a.m. when the market opens, the application is warmed up as good as possible. So there are use cases where you need that. It's not for everyone, just to keep that in mind. Okay, so we saw JVM startup, JVM warmup, what does it mean performance-wise? If we take this knowledge now to microservice environment, that means first time we start a service, we have to go through this optimization curve, okay? Okay, fine. Second run, again. Third run, again. That sucks, right? This is, the JVM doesn't have any memory of its previous run. So that means you started once, it does all the optimizations. The next time you start the service, it has to do it again, right? So it would be great if the JVM could do something like start it once and optimize it. And after that, the second time you start it, just keep all the optimizations and keep it running, right? From the optimized point. And the third time you start it, yeah, just go again. Don't do the performance, let's say, optimization at every runtime. Well, let's take a look at some already available solutions here. First of all, there's class data sharing. Who knows that? CDS, typically are 1, 2. Okay, it's interesting. This is already, per default, enabled since JDK 12. So who's using JDK 8 in the audience, in production? A few, okay. Is someone below JDK 8? Nobody? 11? 17? Some fearless people, 20? No? That's not too bad. So that means if you use 17, you get app CDS enabled per default, if you want it or not. And what it is in principle, to make it very easy, you can imagine you have all your classes and you have the class loader, and the class loader, not only the one class loader, all the class loaders, they load these classes from all kinds of places, means open files, loading, close files, and so on, and load them into memory. So that takes some time. If you can instead load each file just once and store the internal representation in one file of all the classes, then the next time you start up, you just load this one file and you directly have the class representation that you need in memory by loading one file. That's much faster, right? That's the idea. You can share that on JVM starts because there is CDS, which is on JVM level, and there's also app CDS. That means you can even tailor it to your application if you like. That also means there is nothing going on with hotspot detection or optimization or something like that. This is only reducing class loading time. And you can get up to 2 seconds faster startup just by tuning it correctly. And if you would like to know how to do that, then you should check out the blog post from Ionut Balozin, and he's also here at the conference. He had a session. Very informative blog post about how to tune CDS to make it really fast. So, but keep in mind, it happens here. This is class loading time. It's even before it gets into the whole interpretation and compilation phase, okay? So that's good, but doesn't really solve the problem of this performance curve that we saw. The next thing is ahead of time compilation. You probably heard of that. So that means we don't have to interpret bytecode. There's no analysis of hotspots. There's no runtime compilation of code. We can start at full speed straight away, right? Perfect. GraalVM native image does exactly that. So does that solve a problem? Well, not so fast. First of all, who's using GraalVM here in production? Native image. Nobody? Or is there one hand maybe? I couldn't really see it. Okay, so AOT is by definition static. So that means the code is compiled before it is run. So you can only do static analysis on the code. That doesn't mean it's bad, right? So it's just that that's the only thing you can do. The compiler has no knowledge of what the code is actually doing at runtime. He can just make guesses, right? But he can't really run it and optimize at runtime. There's one thing that can help, which is so-called profile-guided optimization. And in GraalVM, this is only available in the Enterprise Edition. And what it does is GraalVM also comes with a JIT compiler. So they run the code using the JIT compiler, profile it, you apply some workload. Once you're done, you use this profile. And when you create the native image, you apply this profile to the native image. And then you can get more performance. But like I said, this is only available in the Enterprise Edition. If we take a look at the performance graph again, now with the AOT approach, then this is more guessing because this really depends on your application. But usually you can say you can reach up to 60, 70% of the performance, plain AOT, no profile-guided optimization. If you use PGO, then you can get up to 90%, sometimes even reach the JIT. It depends. But keep in mind, you have to do the profiling first, right? Okay, and it's only available in the Enterprise Edition. So I found this benchmark, and this is not related to the whole startup time, but it contains some interesting facts. So it's on Beldung.com, which is a quite popular website, and they compared Spring Boot versus Quarkus on JVM level and the native image. So they did the same application, compiled it in both frameworks, run it on the JVM, run it as a native image. You can see the startup times. On the far left, this is the Spring Boot JVM. It was 1.8 seconds, roughly, and Quarkus 1.2 seconds. The native image started up in 129 milliseconds, and Quarkus won in 110 milliseconds. That's really impressive, and that's really fast, right? We all agree. The thing that really was interesting to see is in the last row, it also showed the requests per second that the application was able to handle. You see on the left side, like again, Spring Boot and Quarkus JVM, on the right is the native image. Spring Boot, the native image only got to 74% of the performance. Quarkus only got 53% of the JVM version. So that means using this, because Spring Boot and also Quarkus, they use also Micronaut. They use the GraalVM Community Edition because this is free. No profile-guided optimization. So you gain startup speed, but you lose performance, which can lead to more cost. If you're really relying on the 100% performance, then you need more nodes or more cores to make it work, right? So you just have to keep that in mind. It doesn't mean it's a bad thing. But you have to keep in mind that, yes, it starts faster, but it might be slower in the end. Just remember that. Okay, if we do a short comparison, then AOT can make limited use of method inlining, which is one kind of optimization, because it can only do it as a pre-compiled step, where the JIT does that all the time at runtime, right? There's no runtime bytecode generation in GraalVM, where it is in the JIT. We have reflection is possible in GraalVM. It gets better and better, but it's still not really the same convenience as it is in the JVM. I mean, reflection never is really easy. You can't use speculative optimizations. This is the stuff that I showed you with the de-optimization, right? This is, for example, the branch analysis. You can't really do that because the AOT compiler compiles upfront, not at runtime. So he can't really profile at runtime how the code is behaving, right? So the JIT does that all the time. The overall performance will typically be lower. We saw that already. And the biggest pain point that I see is that the deployment or the environment for deployment is different from the development environment. So you go from a Java environment as a Java developer and step into the native world, right? That's nice for a startup. This really sucks for debugging because you suddenly have to use other tools. You have to use native debuggers, which is not everyone's favor. So this is the biggest pain point that I see. On the other hand, you get full speed at startup where the JVM really needs more time to start up. We don't have any overhead to compile code at runtime. We have more overhead to create the native image, right? That takes much longer than creating the jar file, for example. And we have a smaller memory footprint because JVM only compiles the stuff that is needed. Every AOT compiler does that. Where the JVM, if you, for example, use a library, it loads all the stuff. Where GraalVM in the native image only compiles the classes that are really needed at runtime. On the other hand, if GraalVM doesn't really know about these classes at compile time, and you will try to call it at runtime, it will crash, right? So it has a back and forth. It's good and not good, so it depends. So the disadvantages of the JIT, it requires more time to start up, CPU overhead to compile code at runtime, and we have a larger memory footprint. Okay. Let's take a look at a different approach. We have a project in Linux called CRaC. Does someone know that or ever heard about it? Nobody? It's checkpoint restore in user space. And it's a Linux project. I already mentioned that. It's part of the kernel since 2013. So that's nearly 10 years already in the kernel. Means it's quite mature. It's nothing really new. And it was made to freeze a running application or container and then save the state to disk. And at a later point, restore this state back into memory. So who knows what checkpoint restore is in the audience? Let me give you a very simple explanation. I think the most of you have a laptop, and once you work the day, and then in the evening, you just stop working and just close the lid, right? And then what happens is the operating system detects that you close the lid, it will save all the state onto the disk, including your applications that are open. The next morning, you open it up again, it will detect, oh, there is first of all, it will detect that you open it. Then it will figure out there is a checkpoint, like a snapshot, stored on the disk, and will restore everything back to memory. This is checkpoint restore, right? So, and CRaC is made for this, but for applications on Linux. Okay. It's already used by OpenVZ, Linux containers, Podman, and Docker. So they can use it. It's not the stuff that they use all the time, but you can use it. It heavily relies on the proc file system. That means if you have Linux without support for proc, it won't really work. There's no support for Windows and Mac, but I will come to that later. It can checkpoint all these things. I won't read it because of my voice. You can read it on your own. And it can, this is interesting, it can rebuild TCP connections from one side only, for example. That's quite interesting. And you see it can do a lot of stuff. So, it doesn't come without challenges, of course. So first of all, you can't really take a snapshot from, let's say, this M1 Mac, which is an ARM-based Mac, and then restore that on an x64 Intel Mac. Doesn't really work because different CPU architecture means all the code is not really compatible, so that doesn't work. Also, if I have open files on this machine, I can't really assume that the same files are open on the other machine, right? Or memory, like shared memory. You also can't really start the same instance multiple times on one machine because the PIT, the process ID in Linux, which is unique, is part of this checkpoint. And when it will be restored, it will restore to this PIT. And you guess right that if the PIT is taken, it will crash, CRaC, right? Now, if we take a look at the Java virtual machine, then you would assume this is just an application that runs on Linux. So I should be able to just snapshot that and then restore it later on. In principle, that's true. But again, it's not the JVM. Again, it's your application that makes it more problematic. Because the problem is, the JVM doesn't have the database connection open or doesn't have files open, right? It's your application that has all these open connections or open files. So that's not so easy to do with Creo alone. And this leads me to CRaC, which is the coordinated restore at checkpoint. And the focus is on coordinated. Because what we're trying to solve is, we try to solve the problem that we let the application know when there is a checkpoint, and even when it was restored from a checkpoint, we let the application know that. So why do we let the application know that? Because if you have a database connection open, and you just checkpoint the JVM, it will shut down. Then you try to restore from the files, the JVM will be restored, your application will be restored, it will start running, and then you will try to access the database and it will crash because the database connection is gone, right? The JVM was shut down. So somehow we have to find a way to let the application know, now's a checkpoint, close the database connection, now you got restored, restore the database connection, right? This is one example. So what we do is we bundle Creo with the JDK, and that makes sure that we have the same Creo version everywhere. The heap is cleaned and compacted. We use JVM save points for that. That's the same that is used for garbage collection. So you can be sure that the heap is completely compacted and cleaned, so everything's in the trash that could contain some data that you don't want to have in the checkpoint. It comes with a pretty simple API, but we'll come to that in a minute, and you can create checkpoint using code or JCommand. Who knows JCommand, by the way? Yes, a few people. That's good, because it's a quite powerful tool. Most people never heard of it. And it also throws checkpoint exceptions. So that means if you do something wrong or you forgot to close something, then this CRaC project will tell you by throwing an exception and says, in this class, there was a problem. You might want to look into that. Okay, we added 2 new commands to the command line. CRaC checkpoint 2 equals path. And the path, in principle, the only thing that we do is you tell the JVM when you start up your application, in this folder, you should store the checkpoints in case there is one. Someone will trigger a checkpoint and store the checkpoint in this folder. That's the main idea. Could be a drive, could be a volume, whatever. It's just a path. And to restore it, you call it with Java -XX CRaC restore from, and then you point it to that folder, and then you can restore it from there. That's the main idea. Okay, so it's an OpenJDK project. We started that for, I think, 2 years ago, and it's led by one of our engineers, Anton Kozlov, so you can look it up if you like. We also will make a JAP out of it, so it's in the making. So we hope it will, at some point in the future, will be part of the official OpenJDK distributions. At the moment, it's just in this project. Leads me to the API. The API is pretty simple. We just have one interface. It's called resource. It only has 2 methods, before checkpoint, after restore. It's pretty self-explaining. So we use these resources to notify classes that need to be notified in case of a checkpoint, right? So these classes implement the interface, and then the application receives callbacks when there is a checkpoint and when there was a restore. Okay, so that makes it possible for you to close resources and restore resources. So this is maybe the drawback with CRaC. You have to change the code. Not a lot, only in these places where you have open resources. And there might even be a better solution in the future when we get better framework support, where then the frameworks will take over this whole closing resources, reopening resources, right? Micronaut, for example, can do that already. So that means you have your resource, you need to register that somehow into the JVM, because only by implementing the interface, the JVM has no idea what interfaces you implement somewhere. So to make sure the JVM informs these classes, you have to tell the JVM, okay, this resource I would like to register in a so-called context. The context is only one context per JVM. You can get it by calling core.getGlobalContext, and then you can just register it. So it works like this. You implement the interface, right? Then you get the global context, and then you register this resource into the context. Usually you do that in the constructor of the class, or if you have a factory method, you do it in there. Okay, I already said it's just one context for the whole JVM, and then the JVM keeps track of that. Creating checkpoints is easy. There is either jcommand in this case. You can call jcommand, which is part of the JVM. You don't have to download it or something. Either you call it with the jar file name, or you use it with the PID. So if you run it in a Docker container, usually you use the PID, because it's always the same for the first application. And then you call it with the command jdk.checkpoint. And this will trigger the checkpoint mechanism in the JVM. Okay, you can also do it from code. So people sometimes ask, okay, why do I want to do that, right? So why would I like to do a checkpoint in the code? The default behavior is that the JVM will shut down after the checkpoint. We have a flag that makes it possible to keep the JVM running. So that means you can run your code, and at some point you could, for example, use a REST endpoint or whatever to trigger the checkpoint, and then it will store the files into that given folder, and then whatever you do with that. You can, for example, store it in a volume in your cluster and keep the application running. The next time you start the service, it points to that volume. If there's a checkpoint, restore it from there. Stuff like that is possible, right? So this is the reason why we also have it in code. The question is when to checkpoint. This is a tricky question, because do you know exactly when your application is totally warmed up? Probably not. Some companies know that, like I told you with these trading companies, they are really picky about that. They know exactly when the application is warmed up, but a lot of companies have no idea. And to be honest, most companies don't care. If it works, right? So, but to figure that out, what you can do, you start your application with this parameter, -XX colon plus print compilation, and it does exactly what it says. It just prints out all the compilation steps on the console. And it looks terrible, right? Because once you start it, it's like, it's scrolling like crazy. Doesn't matter. You apply a typical workload to your application, and then you will see that over the time, this number of compilations per second, let's say, it will be ramped down. It will be slower and slower. And that means most of the code is now compiled and optimized. So this is then a good time to create the checkpoint. We're also working on some kind of a metric. So because the JVM loads all that stuff, right? So the JVM knows what was optimized and de-optimized. So we thought about an idea that the JVM might be able to give you like a flag. You can ask, is it good for a checkpoint? And it says yes or no, or true or false, right? So this is something we are working on, at least to make it easier for you to figure out the point in time when to create the checkpoint. Typical usage. Usually you would like to run that on a microservice environment. You can also use CRaC for whatever application you have to restart a lot of times and which takes some time. You can use that, of course, right? Keep in mind that the checkpoint files is more or less a heap dump. So if you have a large heap, you have a bigger checkpoint file. That's the consequence. So what you do to run it in a Docker container, you run your app in a Docker container, you log into that container, create the checkpoint, or you can also do it using the REST endpoint and in-code stuff. And then you store these checkpointed files either in the container, I wouldn't recommend that, but you can do, or you store it on an external volume somewhere, which is the more appropriate approach, I think. And then you commit the state of the container only if you have really stored it into the container. And this is also the reason why I don't really like it, because you don't want to really change the state of the container. But in principle, if you put it in the container, then this is the new state is your new deployment container. Right? This is the one that you use to deploy into production. It contains the checkpoint. Otherwise, you just point it to a volume in your cluster or wherever you run it, and then when it starts, it loads the checkpoint from there. Then you start the container, and like I said already, it will just use the checkpoint and restore to memory. This is only available on Linux, x64 and ARM64. And what about Windows and Mac? Well, who's running a production server in Windows here? There, one? Because some people do. Who's running a production server on Mac? Nobody. But I guess on Linux, most of you, right? So you see, this is not really the big problem. The problem is You as a developer, who's using a Windows machine for development? Okay. A Mac? C. If there's no JVM that supports CRaC on Mac, how would you do that without getting an exception? So we created a little library, which is called org.crack. And you can get it via Gradle or Maven. It's on Maven Central. And what it does, it shadows the complete CRaC API from the JVM. And that makes it possible, if you just add this dependency to your project, you can code against the CRaC API. And it will figure out that if it runs on the JVM that supports CRaC, it will use CRaC. And if not, it will just do nothing. So you can code on Windows and Mac and Linux. And once you deploy that on a Linux machine with support for CRaC, it will use it. And otherwise, it won't just crash. You can use it on your IDE like a normal dependency. You can get more information here about this library. It's github.com/crack org.crack. Okay, so this is also the reason why we are a little bit not sure if it will make it ever to the official OpenJDK builds, because this is not really cross-platform, right? So it works on Linux. It doesn't really work on Windows and Mac. We could make it work if there would be something like CReU on Mac and Windows, but there is nothing really that you can compare. Okay, some words about compatibility. What I mean with that is, I already told you can't really mix stuff like ARM and x64 code, but even if you stick to x64, you have these Intel machines and they started I don't know what the names, but there was something like Core i3, right? And then it was Core i5, then Core i7, Core i9. This is not the only thing that makes the difference, but it's so-called CPU levels. And these CPU levels have different abilities to optimize code. And the JVM knows about that. So if you compile something on a Core i9, the JVM will use the optimizations for this CPU. If you then take this code, try to run it on a Core i3, it won't work, right? Because this CPU, the older one, doesn't know about the new optimization possibilities of the Core i9. This is not really bound to this Core i stuff. It's really the CPU levels. But this is, if you try it with these different CPUs, you will see. So I tried it to run something from a Core i7 on a Core i9. That's no problem at all. Even if you use a Core i5, create the checkpoint there and run it on the Core i9, it will work. It won't use the highly optimized code for the Core i9, but the differences are also not that huge, right? So that's what I said. Downgrading is not possible. Upgrading is no problem. We are also working on a solution for that. I tell you that because if you run something in Kubernetes or in a cloud environment like Azure or AWS or whatever, then usually you have something like so-called node groups. These node groups, you can define the CPU architecture. And then the cloud provider will make sure that for this node group, the CPU architecture is the same for all of the nodes. So you have to make sure that you use the same CPU architecture that you used for the checkpoint. The problem is that in Kubernetes, you can run different node groups in the same cluster. So you have to be careful with that, right? But this is something you have to keep in mind. Once you run that on virtualized Linux environments like Docker, you can run a Docker container that you created on Linux, you can run it on Mac and Windows. That works, as long as the CPU architecture is the same. But that's no problem. Okay, let me give you a little demo. And this is just a name service, pretty simple. It loads 258,000 names when it starts up. I would never do that, but for the demo, it's good. I load that from a JSON file. And then I return 5 random names for boys and girls. That's the main idea. Okay. So, yes, girls and boys. So this is the code, pretty simple. We have the constructor. And you see it prints out start without CRaC. Then I register the resource. I don't have to in this case. I just do that to show how it works, because I don't have really any open resources here. And then I call the init method, and you see the init method just loads all the files. That's the method that loads the 258,000 files from the JSON file, the names. And then it prints out the random girl names and boy names. And after that, it tells us the time it took for the whole process. So this is when I started up without CRaC, just as normal. Then you see already the methods before checkpoint, after restore. If we take a look in the after restore method, it's more or less the same code, except I don't have to call init. Because when I create the checkpoint after I ran through the main method, it's already loaded. It's part of the heap, right? So I loaded that into my map or whatever, so I don't have to load it anymore. I can directly print the random names, right? Clear. I guess this is not really hard. So this is the main idea. So if we take a look, I just do it here. We have on the left side, this is the version that I just run the jar, calling the main class. And then on the right side, I pointed to this folder where I have the checkpoint stored in the CRaC files folder in this case. Okay, when I started up, oh, what's that? So on the left side, you see the JVM startup time was 20 milliseconds. This is really the JVM itself, because you can use JMX beans to ask how long did it took to start the JVM. And then it prints out the start without CRaC. Then we have the loading. That took 1.3 seconds, roughly. And then it prints out the 5 random girl and boy names, and then it says it's 1.3 seconds, okay? On the right side, we don't have to load the files. And you see it directly can give me the random names. And then the startup time was 48 milliseconds, because everything's already there. I don't have to load these names anymore. I agree you never would load these names every time you start up the service. This is just to give you an idea that you really can save some time, because you don't have to do stuff that you usually have to do when you start up your application, right? So it can really improve startup time a lot. But or if you would like to see this example, which is pretty simple, but it gives you a good way to start, then you will find it on my GitHub account. Framework support. There is support in Micronaut. It's the best support so far. So they, for example, can close JDBC connections automatically and reestablish them. So you don't even have to do the implementing the interface, closing the resource, open it again. It's done by the framework, and that's the main idea. And they will improve it over time. There will be more. Then there's Quarkus. They only have very rudimentary support, so that means they only implemented the interface, so you can use it, because they rely on this org.crack API library that I showed you. But you have to implement everything on your own, like implementing the interfaces and so on. Spring will get full support for CRaC with Spring 6.1. They announced it at Spring I/O, and we expect it to be public end of the year, probably. And that means if it gets to Spring, it will also be part of Spring Boot, because that's how it works. Okay. Now I showed you this very amazing demo, right? And not even live, but only on slides. The question is, how good is it really? We did some tests, and you see we have tests with Spring Boot, Micronaut, and Quarkus. And these tests have been done before we got the support, so we had to hack it a little bit. So what we did for Spring Boot, we used the Tomcat server, patched it with the CRaC stuff to make it closable and all that, and then pointed Spring Boot to the Tomcat and said, use this one, right? So this was the startup time for Spring Boot application, around 3.9 seconds, roughly. Micronaut 1 second, Quarkus 980 milliseconds, and then we also did something XML transform just to have something really long, 4.3 seconds. This is OpenJDK without any support for CRaC. And then we did the same, restoring from a checkpoint that we took after this, right? You can imagine at the end of the bar, we created the checkpoint. And then we just restored it from the checkpoint, and that took this time. Same application, it's just continues running. And you see the startup times increased dramatically. So we by a number of magnitudes, so for example, the Spring Boot app restarted in 38 milliseconds. Micronaut 46, Quarkus 33, and the XML transform 53 milliseconds. You might ask yourself, why are they all so close to each other when the original startup time was so long? Because we don't have to start up anymore. This is really loading back from disk into memory, and that only relies on I/O speed. So the faster the SSD, the faster the restore. If you load it from, let's say you have a Redis cache and you store the checkpoints there, you can also restore it from there, even faster. So we get into the native image startup time by keeping the complete JVM. That's the main idea. Even after the JVM started or was restored, if the code changes, it will optimize and de-optimize, right? So this is the main advantage here. Summary. So CRaC is a way to pause and restore JVM-based application. It doesn't require a closed world, as with native image, so we don't need to know what's going on at runtime because it's just a JVM. It's extremely fast, time to full performance level, no need for hotspot detection or method compiles, decompiles, because this is done before we create the checkpoint, right, at the startup phase that we saw. We have improved throughput from the start. It's an OpenJDK project, and it even can save you some money. If you run something in the cloud, you probably know this graph. On the y-axis, we have CPU utilization. On the x-axis, we just have time. And you see this peak in the beginning. And this is usually JVM startup time. That's the time to first response. And this is interpretation and compilation overhead, right? So and you see we need maybe 100% CPU just to make that work. But once it's done, the CPU utilization drops, in this case, maybe around 45% or 50%, whatever. If we create the checkpoint here and then start the next time from there, you don't need this much CPUs, because then we can run the same stuff just by using, let's say, 50% of the CPU. And that can save a lot of money, right? So and you can create the checkpoint on a small machine, because when you create the checkpoint, there's no need to really have it on the fastest machine ever, right? That means it can eliminate the startup time. It can eliminate the CPU overhead. So if you want to know more about it, there's everything you want to know, github.com/CRaC. You will find the implementations, the code, everything's there, it's open source. If you would like to play around with it, we already have an officially available JDK that supports CRaC for Linux x64 and ARM64. You can download it at azul.com. And is it a supported version? This is no pre-build, right? So this is not some like beta version or something. This is an official build that we TCK tested. It's ready for production. And we will also keep new updates coming for these CRaC builds. So if you go to it, use it in production, it's free. So you don't have to charge us or something, so we won't charge you. So it's really just free for use, also in production. There's commercial support. That means if you run into problems and you need support, you have to pay for it, but then we also can get that one. Support for x64 and ARC64, I already told that. And if you need it for JDK 8 or 11, if there's a high demand, we will also create this JDKs. At the moment, we only do 17, but if companies will come to us and say, oh, we need to run JDK 8, then we probably also will create builds on JDK 8 and 11 that have CRaC inbuilt. There's a forum on fuj.io. If you have problems or run into trouble, you can check that out. We just started it, so don't expect there a lot of information right now, but it will hopefully fill up. And with this, thanks for attending, and we have 50 seconds left if there are questions. If not, just catch me after the session. Thanks.
Hello, I do have a question. Right here in the front.
Yeah.
Hi. So regarding the new versions of the code, you mentioned that the optimization would occur. So we can use a checkpoint on a newer version of a code with a bug fix or a new feature, and then when it runs through the new code paths, it will just de-optimize and eventually optimize those, and then we can create a new checkpoint for the new version.
This is possible, yes. In principle, yes. You start from one checkpoint, but the problem is if you restore, you have to think about it. This is a JVM. You stop it, you save the whole state, you start from there. That means if you do a new deployment, you need a new checkpoint if you start from there, right? So you can't just do a deployment of the code and then restore from the checkpoint. That doesn't work. It comes bundled, more or less, right? So it's stopping the JVM and restarting it. That's the main idea. But you don't have to create the checkpoint all the time, only when you go to production. The code will also run without checkpointing and restoring, right? So usually what you do is you run the code, you do some new deployment, test it. If you think, oh, it works everything, then you go to your CI/CD for production, create the checkpoint, and then deploy the checkpoint. And in production, you directly start from the checkpoint. That's the idea.
I see. So it's not necessarily for newer versions, but rather if you have, I don't know, hundreds of replicas,
yes,
you can restore.
That's the main. If you have lots of the same service have to start up at once, that helps a lot. Also, if you have an application that you have to start up all the time, let's say 5 times a day, and it takes minutes to start, it can help you there, of course.
Yes, thank you.
Mm-hmm. Time is over. Okay.